waiting on the computer, so it wasn't turned on yet. So just a minute. Still waking up. Well, good morning there. I'm waiting on my computer to come on here. The power wasn't on this morning, so it's taking it just a little bit longer, but it's getting there. It's I think getting ready to load up here. It is loading up, but let me get logged in here because I want to show you first something on the My Math Lab part you may have already seen, but I want to just make sure we're all aware of what's going on there. And then we'll be looking at homework questions that you had from page 376 for a few minutes. So if you had questions there, just be prepared to ask a few things on that part. First thing we're going to do, though, is go over here to, let me switch to the computer screen. We're going to our D2L site for just a moment. And I want to remind you that there's that link there for My Math Lab. So and then we'll go into My Math Lab, but let me just pull that up here. See, this is you guys here. So remember, you had that information about My Math Lab here. I just want to remind you that that's out there. You need to be getting signed on if you haven't already. A lot of you have already, but just as a reminder, let me put that back out there. And then if you go over to content, you have that link to My Math Lab from content. So right here, if you click on that, it'll take you to the login screen for My Math Lab, or where you can register, either one, if you haven't already registered. And so I'll sign in there just a moment. Started out with the wrong password. Okay, so whenever you go on there, and now if you've already registered, when you go into your class, into our class right here, there should be 4 of the assignments up for you to do, 4 of the so-called quizzes, okay? They're not very long, but you'll want to practice with those. And what I decided to do is, I don't remember what I told you before, but I'm going to just leave those open all semester so that if you want to go back and practice with them before time for the final exam. Oh, this is a problem. I forgot, in here we have trouble loading this, don't we? That happened in this class before. I don't know why. Anyway, you'll have 4 quizzes there. They're listed under the little tab at the left from the main page that says quizzes and tests. There are no tests there, but that's just what it says, okay? Quizzes and tests, but the first 4 are opened up. They're all from chapter 6. We haven't covered everything that's on all those yet. You should be able to be working with the first 2. They're not very long. If you go in and do some of them, I believe that if you have to leave, you know, somebody calls you and you got to go somewhere or something, I believe that you can come back and access from the point that you stopped at. So if anybody sees differently on that, let me know, okay? What's that? They're not timed. No, they're not timed. So just go in, work on them. I mean, you'll have your resources at home you can use as well to help you with those things. You can take them an infinite number of times if you wish. Okay, as far as grading, it'll use the highest grade you get. So you can do those over and over. I'm leaving them open until the end of the semester. Actually, they're going to be due December 7th at 11:59 p.m. is what it's set for. So December 7th, and then that's right before final exam week. Okay, final exams start on the 8th. Your all's is, I don't remember, I think the 9th. Okay, but anyway, right there up to final exam week. Any other questions about the My Math Lab exercises? Yes, go ahead.
So will we have quizzes in class, or will it just be on the My Math Lab?
It's just on the My Math Lab at this point, okay? We may have one in class later on, but right now it's just a My Math Lab, okay? I will let you know if we're going to have something in class. All right, so any other questions there about getting on the My Math Lab stuff? There's 4 quizzes open. They'll be open all semester. That does not mean that I'm inviting you to procrastinate. I'm not. I don't want you to procrastinate, okay? Try to work on those while we're in Chapter 6. That would be ideal. All right, I'm sorry I couldn't pull that up for you after all here. I don't know what's wrong with that. Somebody in my other class said that it does work better from using it if you're using Internet Explorer as your browser. So if you try something else, you know, Chrome, Firefox, whatever, and it doesn't work, then go to Internet Explorer, because they're telling me it works on that better. All right, well, we tried. We couldn't get that working. So let's go then to questions you might have about the material we've already looked at on the trigonometric functions. Last time, we were looking a little bit more at that unit circle. We were looking at the coordinates associated with the terminal sides of the angles and how those were related to the sine and cosine of the angles involved. We looked at all 6 trig functions, those ratios, y over r, x over r, those things, right? Okay. Does somebody have a question from the part we were looking at, something you'd like to look at? Go ahead. Yep, you. I saw you were getting ready to
Could you do question 39, please?
Yes, 39. So 39 is over on page 376. Four sine 90 degrees minus 3 tangent 180 degrees. So I'm just going to draw a little diagram here of at least part of a unit circle. I guess we'll put the whole kind of circle on. Okay, bad circles this morning. So 90 degrees is up here. The coordinates associated where the circle hits that y-axis there, my circle's really bad up there too. The coordinates associated up there are what? 0, 1. Okay, 0, 1. That might be what's going on there, right? Okay, because it's 0, 1 because we didn't go anywhere on the x-axis. We just went up 1 on the y-axis. Okay, so 0, 1. And so therefore the sine of 90 degrees is 1. And we already have this 4. They're going to be multiplied. When 4 is sitting right next to the sine of 90 degrees, I know that means 4 times the sine of 90 degrees. Okay. Then we have minus 3 times something here, but let's go over and put on our 180 degree angle. So that would be around to 180 degrees if we go there. The coordinates over here are what? Negative 1, 0. The tangent of 180, let me just write down here, the tangent of 180 degrees is going to be the y coordinate over the x coordinate, y over x. So what's that going to equal? 0 over negative 1, which is 0. All right, so the tangent of 180 is 0. So we have 4 minus 0 will be 4. Okay. So that's what we're doing on that part. And these exercises were trying to help us get a little bit more familiar with our trig function values on that unit circle. What else there from what we were looking at? Yes, go ahead.
Could you do number 21 or any of the other ones in that first section?
Okay. Let's go over here to 21 or any of those, right? So do we want to just start at 21 maybe? Is that all right? Sine of 11 pi halves. Okay, again here, we're looking for the trig function values, but what we see is that whenever we have angle measures like 11 pi halves, which we know that's a pretty large angle, you know, if we want to go back to degrees, some of you may have done that and converted, you would see that's a very large angle. But what we're doing is we're keeping on wrapping around that unit circle to get these values. The sine of 11 pi halves will be the same as the sine of one of our angles, one revolution around the circle, because they'll have the same terminal side. Okay, essentially they'll have that same terminal side. So let me draw again. Now we're on a unit circle, so remember that's one there, that's one there. And -1 and -1. Sine of 11 pi halves. If I start here, I'm starting at 0, and if I go all the way around, I go 2 pi units, right? Now 11 pi halves, the way we might want to look at that part is that that's 5½ pi. We do not normally write angles in this form, that we don't normally write mixed numbers with the pi. But for thought purposes, it makes it a little easier for us to think about. 5 pi, let's just start thinking about 5 pi is going to end the same place as which angle on my original unit circle? As pi, right? So if I go around to here, what's happening is here, I go around once, I'm at 2 pi. I go again, I must be at 4 pi. So over to here is 5 pi, but I need 5½ pi. So where's this one going to end? Okay, at 270 degrees, or in radians, that was 3/2 pi, or 1 1/2 pi, right? We went another ½ pi there, past the 5 pi area. So the sine of 11 pi halves is going to be the same as the sine of 3 pi halves, which we can see a little more easily. The sine of 11 pi halves will be the same as the sine of 3 pi halves. This has to do with the sine function being periodic, and it's 2 pi periodic. What that means is every 2 pi units, the trig functions will be the same. They repeat themselves. Okay, so sine is what we call 2 pi periodic. So we keep going around, and we're seeing that as we wrap this function around here. Sine of 3 pi halves then is going to be what? What are my coordinates down here? 0, -1. So the sine there is -1. Okay. So we're wrapping the function around to get there. Yes, you had a question?
On those, you said we can convert it to radians.
If you really want to convert it, you can, but I'd like for you to start thinking about it in terms of radians. But if you need to convert it to kind of see where you're at, you could convert and then, kind of mix back and forth, make those connections.
I know this sounds crazy, but is it 2 goes into 11 5 times, and then you take 11 minus 10, and that equals your 1/2?
Right, that's right. So 2 goes into 11 5 times with 1 left over, so it's 5 1/2 pi. That's correct. Let's look at another one from that part just to make sure we got that, okay? Does anybody have a specific one in that 21 to 30 area? Okay, so y'all want me to choose. So let's see. Let's do, I'm actually going to choose one that might be an even one here. Let's see. Well, I thought I was. Let's do 30. The tangent of -3 pi. Maybe that one's not so bad because it's not fractional, but it is negative, so I thought it might be worthwhile to see a negative value. And this is still a unit circle here is what we're dealing with. So tangent of 3 pi. I know I've got 0 there, pi, 2 pi, but now I'm going negative. So when I go negative, where do I go for 3 pi? I got to go clockwise now, so this would be 2 pi all the way around, right? -2 pi, I'm sorry, -2 pi. And this puts me at -3 pi. So -3 pi is going to end at the same place where we have pi. So that's going to be the same as the tangent of pi, or for that matter, the same as the tangent of -pi, isn't it? Either way, we could look at that. Same as the tangent of pi or -pi. All right, so the coordinates over here are -1, 0. So what's the tangent going to be? 0, right. 0 over negative 1, so that is 0. So maybe that one wasn't as bad as 11 pi halves. I don't know. Maybe not so bad. But we want to see that these angles that we're looking at in that part are ending up at the same places as some of the angles we first saw in the first revolution. In the back there, I'm sorry, you had a question?
Yes, so it doesn't matter if you use negative pi or just pi?
In this case, it does not matter because they both end at the same place. Negative pi or positive pi both end on that left side of that x-axis over there. It may matter on some of the others there, okay, depending on what you're working with. All right, so what else from this assignment? Yes?
Can you go over to 41?
Yes, so 41. 2 sine pi thirds minus 3 tangent pi sixths. So every screen, I'm drawing a picture here. So we'll have a little diagram of a unit circle. Pi thirds, that's the same as your 60-degree angle. So put pi thirds right here just to note that's where it's ending. Up there, it's actually this angle here. Pi sixth is the 30-degree angle, so it's right here. We have coordinates out here with both of these. So on the pi sixth angle, what are my coordinates here for the pi sixth? Square root of 3 over 2, 1/2. That's correct. And up at pi thirds, they are 1/2 square root of 3 over 2, right? The reverse there. So notice all these coordinates we're working with in our unit circle, they're either the square root of 1 over 2, the square root of 2 over 2, or the square root of 3 over 2. But the one that's the square root of 1 over 2, we just call 1/2. Okay, but they're all either square root of 1 over 2, square root of 2 over 2, square root of 3 over 2. Those are the numbers you're remembering up there. Just got to put them in the right places. All right, so the sine of pi thirds, what's that going to be? Square root of 3 over 2, and it's times that 2 out front, minus 3 times, we want the tangent of pi sixth. So the tangent of pi sixth, it's going to be the y over the x. So that simplifies to be 1 over the square root of 3. And you went ahead and rationalized it, didn't you? Over here, I heard. So square root of 3 over 3. Looks like what we have there. So we had the 1/2 over square root of 3 over 2. They both had 2's in the denominators, which means when we flip that bottom one and multiply, then those 2's are going to cancel out. We have 1 over the square root of 3, and we rationalize and get square root of 3 over 3. When we take it back up to the problem, those 2's cancel, so I just get square root of 3 minus those 3's cancel, square root of 3, and the square root of 3 minus square root of 3 will be just 0. Right. Just 0. So these are good problems that while you're trying to learn these things on your unit circle, you might want to have that unit circle handy either on your computer screen or print it out next to you to look at these values and see what the sine of pi thirds is or the tangent of pi sixths. It just makes it easier to see. And hopefully then these coordinates will start sticking in your head a little bit better. Yes?
Can you say we're going to get a blank unit circle on the first test?
Yes, you will have a blank unit circle on the first test as part of your test, actually, but then you can use it, right?
Right.
So as long as you fill it in correctly, it'll be very useful. So you want to know that unit circle. Now, the way you can start practicing with that, remember I posted a blank unit circle on D2L. Print it off, see what you can fill in. You also have the filled in unit circle on D2L. Okay? Compare it, test yourself before test time. All right. I think on Tuesday, let's see, we also worked with some of those later ones where the radius was not equal to 1. So maybe we need to look at one of those as well. Down there, does anybody have a question on one of those problems? Yes, go ahead.
Can you do 79?
Yes, 79 works. So the coordinates are 2, -3. And we said the deal here is that at 2, -3, we have a point that's on the terminal side of some angle. So we got this going on here, okay? And that's the point 2, -3, which means that that's the point that would be on some circle we would draw in here. And that point, from the point up to the origin, that's going to be our radius for that circle. Now the radius is important because we know that x squared plus y squared equals r squared on these, within the circle, on these triangles we're forming. What we want to always think about, though, is the right triangle that's formed when we connect that point back up or back down to the x-axis. So essentially what we're looking at then is going to be this angle here, theta. Even though overall our initial angle would have been all the way around there, okay? Now that initial angle that I drew all the way around there, though, it's going to have the same trig function values as the negative angle theta that I just put in there because they end at the same place. They have the same terminal side. And that's what we're looking at here with some of those others as well. So we want to draw that triangle and focus on that part. We got a little right triangle here. What do we know about our triangle? X equals 2, y equals -3. I'm writing them there to show, you know, that's the measure of those two legs. That's the measure of the two legs. We want to know the radius so that we can figure out the trig function values for the angle. The cosine, remember, would be x over r. The sine would be y over r. So we need that r value. We know x squared plus y squared equals r squared. So we've got 2 squared plus -3 squared equals r squared. That's 4 plus 9. So it's looking like r is going to be the square root of 13 here. R is the square root of 13. And then knowing that, we have all the information we need to get our cosine, sine, tangent, cotangent, secant, and cosecant. Are we okay so far? Does anybody have a question so far of what we're doing? All right, great. X over r, 2 over the square root of 13. Normally we rationalize these, so let's go ahead and rationalize. We'll get 2 square roots of 13 over 13. And we're looking for exact values here, so we're okay with leaving it in radical form. We don't need the decimal approximation. The sine is y over r, so we will have y is -3. R was the square root of 13. So that's going to be, if I rationalize that part, and I'm just writing this in so you can see what I'm doing to rationalize, -3 square roots of 13 over 13. Tangents y over x. So we have -3 over 2. Okay. Remember we were given x and y up there at the beginning. Anyway. Cotangent's going to be the reciprocal of that tangent. So it's going to be -2/3. Which one did I say the secant's the reciprocal of? Of cosine, right. The reciprocal of the cosine. Well, let's look back up there at the reciprocal of the cosine a minute, because when I look at the cosine, first I'm seeing this last thing I got up there, but if I reciprocate that, I'm going to have to rationalize. What if I go back and get what I first had for the cosine? Remember my first value I put down for the cosine? That would make my life a little easier now, wouldn't it? Let's reciprocate that first one. So we want to say that's going to be square root of 13 over 2. So we want to look back at that first part, and then we don't have to reciprocate. I mean, we don't have to, not reciprocate, rationalize again, the wrong R word. We don't have to rationalize yet again. And the cosecant of theta is the reciprocal of the sine. So it's going to be, again, we might want to look back a little bit before we rationalized up there on the sine. So what are we going to get here? Negative square root of 13 over 3, right? Negative square root of 13 over 3. Here's something else we're noticing here, okay? The r value, the radius, is always positive. Always. The x and y's, though, they could be positive or negative because they're coordinates on the xy coordinate axis, okay? So we want to notice that stuff as we go through. Because the x and y's are positive or negative, whichever the case may be, because r is positive, we get different signs on our trig functions. Some are positive, some are negative. What does it depend on? Which quadrant they're located in. It depends on the quadrant they're located in. So with that in mind, we're going to go a little bit into section 3, okay? Because that ties in with part of section 3. There are some things in section 3, though, that I'm leaving till we do the graphing of the trig functions, okay? We've not done the graphing yet. This is unit circle information, but when we actually do graphs, then I'll talk about the domain and range of the trig functions. But today I want to focus on a little bit on some of the other properties of the trig functions out of chapter section 6.3. Keep saying chapter. So we just said, you know, the trig function values are going to depend on which quadrant they're located in. So let's look at that just a little bit here. Now we know in the first quadrant that the signs of x and y are all positive. So I'm going to put my ordered pair like that. I'll have a positive x, positive y is what I'm saying there. We know in quadrant 2, what would my signs be there? Negative, positive. Quadrant 3, negative, negative. And quadrant 4, positive, negative. Now we also noted that the cosine is equal to x over r, so the cosine has something to do with the x value. We know r is always positive, so that means for cosine, if the x is positive, then the cosine's positive. If the x is negative, the cosine's negative, right? We can see that stuff. So in which quadrants will my cosine be positive here? One and 4, where the x values are positive. Quadrants 1 and 4. In which quadrants will my sine be positive? Just 1 and 2, right? Just 1 and 2. All right. Where's my tangent going to be positive? Okay, and 1 and 3, where the signs are the same as each other because it's y over x. So where the signs are the same. Now, what do I mean in these quadrants? We're talking about if the angles end in these quadrants. That's what we're saying. If the terminal side falls in quadrant 3, then I'm going to know my sine and cosine will both be negative in quadrant 3, but the tangent will be positive in quadrant 3. Now, there's a little rule that tries to help you remember this. It's called the ASTC rule. The ASTC rule, you can remember it because it stands for all students take calculus. They don't really, but see, we're trying to do a little calculus recruiting here. All students take calculus. Well, here's how we're going to label the ASTC on our quadrants. We're going to label them just like our quadrants are labeled. So this is going to be ASTC, just to help you remember which signs are positive in which quadrants. That's what the ASTC rule really does, is help us remember which signs are positive in which quadrants. So for the trig functions themselves, in quadrant 1, all the trig functions are positive. A stands for all. So I'm going to write out a little bit more here. All trig functions positive in quadrant 1. Because if our x and y coordinates are both positive, then everything we get from those will be positive. Now, in quadrant 2, you told me a trig function that was positive just a few minutes ago. What was it? It must start with S. Sine. Okay? It was the sine we talked about a few minutes ago. So the sine is positive in quadrant 2. Now, it is also true, even though it's not denoted by ASTC, there is another trig function that's positive in quadrant 2. The reciprocal of the sine would also be positive. So what's the reciprocal of the sine? The cosecant. So we just have to remember that one. We have to know in our mind that whichever trig function is positive in that quadrant, the reciprocal is also positive. Okay. That makes sense though, doesn't it? All right, quadrant 3. What's positive down there? You all already told me a while ago, but what is it? Tangent. So down here the tangent's positive. So what other trig function must be positive there? Cotangent is the reciprocal of tangent, so it must also be positive. The ASTC, those just defined by these values here. Now it looks like En. Sorry. We don't have an En, do we? All right, so in the fourth quadrant, the C stands for? Which one? Cosine or cosecant?
Cosine.
Cosine. Okay, cosine. We already said up in quadrant 2 that the cosecant is positive up there, remember? See that one? We've already taken care of that one. Quadrant 4, the cosine and the secant will be positive. So in ASTC, those letters stand for all, sine, tangent, and cosine. So the sine, cosine, and tangent are our 3 most popular trig functions, right? Those are the ones you hear the most about. The other 3 are reciprocals of them. So we're denoting the quadrants, which trig functions are positive in which quadrants by those main 3 trig functions. Now, I've told you which trig functions are positive in those quadrants. What does that mean about the rest of them? They're negative. If I didn't say they were positive in these quadrants, then the rest of them's negative. Does that make sense? They would be? They are. So because you know about this now, you can tell me which quadrant an angle is going to end in, where the end or terminal side will be located. So if I tell you some information here, you should be able to tell me which quadrant the angle ends in. So let's do this one here. This says, if the cosine of an angle is less than 0 and the tangent of an angle is greater than 0, then which quadrant is theta located in?
Quadrant 3.
Okay, I hear quadrant 3. Do you agree? Cosine's negative, tangent's positive. So how do we think about that? Maybe a little process of elimination. You might first want to think about where's the tangent positive. Well, the tangent's going to be positive up in the first quadrant because everything is, but also in the third quadrant. Tangent's positive in first and third. Okay, so we know this part here is happening in quadrants 1 and 3. So let's work on the other part now. But where's the cosine negative? If the cosine has to be negative, then we can't be in quadrant 1. That rules that one out because everything's positive in quadrant 1. So therefore, it must be only quadrant 3. Okay. Let's try now. What can't be negative? Theta could be a negative angle. Yeah, theta can be negative, but we're looking at which quadrant which quadrant's the angle located in. We're not going to specify what the actual angle is, though. Okay, we're not trying to determine the angle. We're just trying to determine where that angle ends at, where the terminal side lies. Let's try another one here and see. Let's do, and these are in your book on page 390, actually. This one was number 32. Let's do number 30. 30 says, this time the cosine's positive. Oh, it says cosine theta is greater than 0, but that means that the cosine's positive, doesn't it? That's what it's telling us. So we might need to note that here. and the tangent of theta is also positive. So which quadrant must the angle theta be located in? Which one? 1. I hear 1. Some of you are getting really fast on this. The cosine and the tangent are both positive. So where's that going to happen? Quadrant 1. Maybe start with one of them. If you're not sure about this, start with one of them and then go from there. First part said the cosine's positive. Where's the cosine positive? 1 and 4. Where's the tangent positive? 1 and 3. Well, theta is theta and will only be in one quadrant. It will only be located in one quadrant. So it must be quadrant 1 then, because that was true for both of them. That's what we're seeing there. Y'all seeing what we're doing? We're looking a little bit better at this stuff now. Just to get our signs. Well, sometimes we need to know, where our angle lies if we're trying to figure out the trig function values, so we'll get the correct signs on the trig function values themselves. So that's why we're looking at this little part right here. Later on, you'll get some information given to you about an angle, and they might tell you, the cosine's going to be negative or something like that. And using that information along with any other information you have, you'll know which quadrant you're looking in. And whichever quadrant you're in determines, the signs of your trig functions. All right, let's put up some identities up here from this section. And again, this is section 6.3, so it's what we just looked at. But let's look at some of the identities. Some of these we have already looked at, but I did not call them identities yet. What an identity means is that one side of an equation is identical to the other. Two things that are identical, and therefore we call that property that they're equal an identity. That's where it is kind of originating from as far as the vocabulary is concerned. So identities, some of the ones we've already seen. We've already looked at the reciprocal identities. The reciprocal identities were where we said that the cotangent of an angle will be the reciprocal of the tangent. The secant of an angle will be the reciprocal of the cosine. And the cosecant of an angle will be the reciprocal of the sine of that angle. Those are our reciprocal identities. We've already put those up there. We just didn't call them reciprocal identities, but that's what they are. One side's equal to the other. We also have what we call quotient identities. Quotient, what does quotient mean, that word?
Division.
Yeah, it means we're dividing something, okay? So the first set of identities, we were doing the reciprocal, or using the reciprocal of something. Now we're going to divide something to get here. So we're going to divide two trig functions. Our quotient identities are these, that the tangent of theta is equal to the sine of theta divided by the cosine of theta. Always, if you take the sine of an angle and divide by the cosine of the angle, that will give you the tangent of that angle. Now we can think about that a little bit too, because we just looked at that unit circle and those ratios. And remember, the sine of an angle was y over r. Remember that? Y over r, but in the unit circle, r was 1, so the sine of the angle was just y. The cosine of an angle in the unit circle was just what? X. So we had already mentioned before that the tangent was equal to y over x, and y was our sine and x was our cosine. So we're just rewriting this kind of in a different format.
So this only works on the unit circle?
This works for everything, okay? I'm just using the unit circle to illustrate that we could see it very easily from there, but it's always true. Because the fact is, no matter what r is, let me make a note over here. Remember we said before that tangent was y over x, right? We also know now that tangent sine over cosine. We know that in general, sine was y over r, and cosine was x over r. So that now we can say that the tangent If we know it's sine over cosine, then whatever those r values are, we take the sine over the cosine, and we see the same thing happening that happened in our complex fraction a few minutes ago, where we can cancel out those like denominators. So we're still going to get that the tangent is y over x, no matter what that r value is. It does not matter. Tangent will always be equal to the sine over the cosine, as long as we're working with the same angle, okay? So the tangent is always sine over cosine. Now, that's a quotient because we're taking the sine of the angle and dividing by the cosine of the angle. The cotangent then is our other quotient identity. The cotangent would be, since we already know that the cotangent is the reciprocal of the tangent, the cotangent will be the cosine of the angle divided by the sine of the angle. Kind of using that quotient identity to allow us to write that part. We know that tangent and cotangent are reciprocals of each other. Okay, we got these. And then we have another set of identities in section 6.3, and they're called Pythagorean identities. When you think of the Pythagorean, or just the word Pythagorean, you probably think of the Pythagorean theorem, a squared plus b squared equals c squared. We've been using x squared plus y squared equals r squared. In general, if we have Pythagorean identities, what we're saying is we're going to square two values, add them together, and they're going to equal something squared. It's going to have that same format. So these are some identities with that same format. Here are some identities that are always true. Sine squared theta plus cosine squared theta equals 1. Sine squared theta plus cosine squared theta equals 1. When you go on into a calculus class, some of you are going to do that, you will use some of these identities to make substitutions when you're trying to take derivatives or work with integrals. These things will come in handy. They're very important to know. Yeah, I won't be giving you these formulas on the test. These you're going to know. More stuff you got to know. All semester long, okay? All semester long. So I'm telling you up front, I want you to know the unit circle. No, right? I want you to know these identities we're looking at right now today. These are things you've got to know. They won't be on the trig formula sheet. Okay, there's other things on there, but not these. The trig formulas that I put on that formula sheet are some things from up in chapter 7 and 8. Maybe just chapter 8, I don't remember. Anyways, nothing from chapter 6 is on there. We want to know everything in chapter 6. All right, so with this Pythagorean identity, this is probably the most popular Pythagorean identity we work with. We see it quite often, in math classes at least, maybe not, every day. But the other two can be derived from this one. So if you forget the other two, if you only remember this one, I'm going to show you how to get to those other two. So this is one main Pythagorean identity. The next one, to get there, I'm going to start with the same one I just have, but I want to rewrite it because I'm going to mess it up a little. Okay. And for this one, what I'm going to do is I'm going to divide every part of the identity by cosine squared of theta. I'm going to divide every part by cosine squared. I'm telling you a way to remember how to get to the other two identities, okay? We're doing one of them right now. So if I divide every part of this by cosine squared theta, I'm doing the same thing to the whole equation, so I'm not changing that it's equal to each other, the two sides. I'm just changing the looks of it. Now, I need you to use some of those identities that I gave you on the previous screen to help figure out what this thing's going to equal now. Sine squared theta over cosine squared theta, what's that going to equal? Right, tangent squared theta. plus cosine squared theta over cosine squared theta will equal 1 equals, and what's 1 over cosine squared theta? Secant squared theta. So this is another Pythagorean identity. Tangent squared theta plus 1 equals secant squared theta. That's a Pythagorean identity. And the other one, again, I'm going to start back with what I had originally. Sine squared theta plus cosine squared theta equals 1. But this time, instead of dividing by cosine squared theta, I'm going to divide by sine squared theta. And so if I take turns dividing my sine squared theta plus cosine squared theta equals 1 by sine squared theta, and then separately by cosine squared theta, I'll get the two other Pythagorean identities. So this time I want to divide by sine squared theta. So what's that going to give me? 1 plus cotangent squared theta equals cosecant squared theta. Okay. Now even these two we just found look pretty similar. You know, one has tangent squared theta plus 1. The other one essentially has cotangent squared theta plus 1. The things they are equal to are cofunctions of each other as well, secant squared theta and cosecant squared theta. Some little things you might want to note here. These are Pythagorean identities. These are the only three there that we're looking at for that. Okay. So what this means then is if I have something like, remember we're not using a calculator, but we can use our properties here. This is number 80 off of page 391. If I have the tangent of 10 degrees times the cotangent of 10 degrees, I can figure out what that equals, even though I don't know a thing about a 10-degree angle and its trig functions. 10 degrees was not an angle that we learned coordinates for on our unit circle, was it? 10 degrees is on there, but we don't have coordinates for it that we know in our head. But we have tangent of 10 degrees times cotangent of 10 degrees. What's that going to equal?
1.
1. Why is it equal to 1?
Because you have the reciprocal times a fraction, and then they'll cancel each other out.
Right, so I'm just going to pick one of them. I chose cotangent 10 degrees to write as the reciprocal 1 over tangent 10 degrees. I still have this tangent 10 degrees out here. They're being multiplied, so these cancel, just leaving me with 1. We're multiplying reciprocals together. Anytime you multiply reciprocals together, you're going to get 1. If I take 5 times 1 over 5, I'm going to get 1. So likewise, if I take a tangent of an angle times the cotangent of the same angle, I'm going to get 1. That's using these properties we just looked at, using those identities. And we don't need a calculator for that either. Okay, so what if we have then, let's put down another one here. Let's do 82 says the cotangent of 20 degrees minus cosine of 20 degrees over sine 20 degrees. Yeah, that's 0, isn't it? Because we've got cotangent 20 degrees, and this cosine over sine business, all with 20 degrees, would be equal to the cotangent of 20 degrees. So that will equal 0. We seeing how we got there? Remember that cosine 20 degrees over sine 20 degrees is the same as, that's one of our quotient identities. The cosine of an angle over the sine of the same angle will give us the cotangent of that angle. Let's put another one up here. I'm choosing 78 here. Secant squared 18 degrees minus tangent squared 18 degrees. You might think about this one a little bit. A little tougher maybe. What was our identity that had something to do with tangent squared and secant squared? It was one of those Pythagorean identities. It said tangent squared theta plus 1 equals secant squared theta. Well, this looks like it comes from that. You know, it's a little different looking though. What's that going to equal?
1.
1. Good. How did you get it? You used a little algebra, didn't you? On the original formula down here. So on this original formula, we see we want secant squared theta minus tangent squared theta is what we want. So I would have to remove tangent squared theta and pull it over with secant squared theta. So I get 1 equals secant squared theta minus tangent squared theta. So what that means is that from these Pythagorean identities, we can, from each of those, we can get 2 more identities. We don't have to memorize all that. You know, you don't want to totally overload up there, but the tangent squared theta plus 1 equals secant squared theta. We recognized we had to use that. We saw if we subtracted tangent squared theta from both sides, just using our equation solving techniques, that secant squared theta minus tangent squared theta would be equal to 1. What's the other one I could get from that information here? If I had tangent squared theta plus 1 equals secant squared theta, what if I would have subtracted 1 from both sides? Right, so the secant squared theta minus 1 equals the tangent squared theta. That must be true as well. Secant squared theta minus 1 is equal to tangent squared theta. So these are 2 more that we've kind of built off of that one. That's true for all those Pythagorean identities. We could do that. We can have them in different forms, different arrangements. So we just have to look for, you know, what's going on with the arrangement there from the Pythagorean identities. It's good you all got that one, though. Very good. Other questions so far on any of these? Yes. So these properties you want to get in your head. These, I'm going to give you some practice problems to try to help you do that from this section. We can also use the properties to get some of the trig function values. Maybe not the Pythagorean properties just yet, but some of the other ones where we know that tangent, sine over cosine, and so forth. So what I want us to look at next is where I'm going to give you some trig function values. I'll start out just giving you the sine and cosine. Would you be able to come up with the other remaining trig functions? I think so now. You've got the tools to do that. So let's see what we can do here. Is everybody finished with this screen here? Are we finished now? So this time, let me give you one like this. The sine of the angle equals 4/5. The cosine of the angle equals negative 3/5. This is 36 off of page 390. So that when you're looking through the practice problems, you'll have an example of something that went on here. And we want the other trig function values. This time they're not giving us, you know, the point, the xy point. They're telling us this is the sine, this is the cosine. Can you find the rest? Well, you can because you know those identities. We know that the tangent will always equal the sine divided by the cosine. And we're given the sine and cosine. So we have enough information here to work with. So the sine is 4/5. Cosine is negative 3/5. What's that going to give us?
Negative 4/3.
Negative 4/3. Great. Very good. We should have it pretty easy from here. We know the cotangent is the reciprocal of the tangent. So it should be negative 3/4, right? We know the secant is the reciprocal of the cosine. So that should be negative 5/3. And we know the cosecant is the reciprocal of the sine. And that will be 5/4. So that's how we would get the remaining trig function values here. We didn't have to draw anything, right? We're just using those reciprocal identities and quotient identities. That's what we're doing there. Any questions on that part? Well, over to the side here, they don't ask you to do this right here, but let's verify. I want you to verify that identity. Sine squared theta plus cosine squared theta equals 1. Because they're saying, you know, no matter what the sine and the cosine are, if we square each of those, add them together, we should get 1. They told us the sine and cosine here. If I take the sine, square it, plus the cosine, and square it, will I get 1? That's the question. Okay, will that left side turn into the right side? Well, I told you to verify it. So you know when I tell you to verify something, it's going to happen. I just want you to see that it does happen. So what's 4/5 squared? 16/25 plus what? 9/25 equals 25/25, which is 1. It definitely checks out, okay? It will always check out. I won't make you check the other two, but this always checks out. That's why it's an identity. It always works. All right, so if we have the sine and cosine, we can find the other trig function values. What if we're given a little bit different information? Let me flip over here to a new screen, but some of you are still writing, so let me hold up just a second here. Maybe I had too much coffee this morning. Y'all think I had too much coffee? Do you? What's that? You all didn't have enough? Or enough time to wake up yet? And we got to get going fast in this class, don't we? 8:15. I don't know, 2 cups of coffee this morning. That's not too bad, right? So, yeah.
So for the this identity with the sine squared plus cosine squared equaling 1, is that because all the angles equal 1 pi in a triangle, radians?
It has to do with the triangle. You're right about that, because here's what we had. You know, we went out x units, up y units to some point on the circle. We had our radius there. In our unit circle, remember the x, y coordinates were the same as saying the cosine of an angle and the sine of an angle, right? So whatever our angle theta is here. So whenever I work with that, we already know that x squared plus y squared has to equal r squared because of this right triangle we've created here, which is the same as saying, you know, my x was my cosine there. So the cosine plus the sine, whoops, let me write it like this first. The sine squared equals, well, what was my radius? Unit circle, the radius was 1, right? So instead of x, I'm putting x was the same as the cosine in that unit circle. Y was the same as the sine in that unit circle. So that's kind of where we built these properties from, but they work everywhere. Okay, we built them from here, but they work everywhere. Now, when I have cosine theta in parentheses, and I'm going to square that, when I have cosine theta in parentheses, and I'm going to square that, the way we write that, though, in trig is normally like this, cosine squared theta. That means I'm squaring the cosine. That's what that means when I have that. So that's something we might ought to clear up also while we're on this part. When I have cosine of theta and I square that, it's the same as saying cosine squared theta. That's just standard way to write that. plus sine squared theta equals 1. So it comes off of this basic unit circle properties is where it comes from. It works, though, for any of them.